All right, last lesson we talked about how to find, or what the derivative was, and how to find the derivative using a limit definition for a secant line that got the points closer and closer together. This lesson we're going to learn some shortcuts to find the derivative so you don't have to use that limit definition every time. The first two rules we're going to learn are called the constant rule and the power rule. We'll start with the constant rule. The constant rule is finding the derivative of a constant function, like y equals, well, f of x equals 7, y equals -2, or h of t equals 28. Y equals a number or some representation of y equals a number. If y equals 7, you have a horizontal line at 7. We've defined the derivative as the slope of a tangent line. So any horizontal line has a slope of 0. So the derivative of any horizontal line is also going to be 0 at all points. So the derivative with respect to x of a constant is always 0. Now you have the power rule. The derivative with respect to x of x to some power. As you go through, and I'm sure you've done some of these in class, and you'll probably do more and a proof of this in class, but the derivative of x to some power, no matter what power, x squared, x to the 5th, x to the 10th, any power, is going to be that power n times x to the n minus 1. Meaning you take the power, bring it out in front, and then multiply that by x to 1 less than the original power. So we'll do a couple of examples here. If f of x equals x to the 8th, f prime of x will equal, well, 8 is your n, so 8 comes out front, 8 times x to the n minus 1. So 8 goes 1 lower, so you're at 7. So the derivative of x to the 8th is 8 times x to the 7th. So any basic power x to a power right away is pretty simple to derive. Now you're going to see other forms of power functions. Y equals the 5th root of x, or any root, any radical function. The key to using the power rule is rewriting the original function as x to a power. So here, we're going to first rewrite it. Before we derive, we want to rewrite it. So y equals x to a power. Well, the 5th root can be written as the 1/5 power. Now, to derive that, you apply the same power rule. Y prime equals 1/5, that power comes down, times x, to a new power, 1 less than the old power. So 1/5 minus 1 ends up being a -4/5. So the derivative of the 5th root of x is 1/5 x to the -4/5. And the other type of function that's common to see can be rewritten as a power. H of t equals 1 over t to the 6th, where you have your power, your variable, in the denominator. So again, first thing you want to write it as the variable to a power. So h of t equals t, 1 over t to the 6th, the same as t to the -6th power. Now you can apply the power rule. H prime of t is going to equal, power comes down, so it's -6, times t to the 1 less power. -6 minus 1 is -7. This was a multiple choice problem. You would probably see the answer as -6 over t to the 7th. You usually don't see negative exponents in your answer. So there's the constant rule and the power rule. Next, two fairly intuitive rules. First one is the constant multiple rule. If you multiply a function by a constant, the derivative will also be multiplied by that constant. So you take the derivative as normal, and if there's a constant out front, you just multiply that by the derivative. So if y equals 5 times x to the 9th, y prime is going to equal, you still bring that power down, just using the power rule, but you also multiply it by that 5, that constant is already out front. So this is going to equal 45 x to the 8th now. simple. You just multiply that constant that was multiplied by the function by the derivative of that function. We have f of x equals 4/7 cube root of x. We rewrite it first. F of x equals 4/7 times x to the 1/3. Then you'll again apply your power rule. F prime of x equals 1/3 times 4/7 times x to the negative 2/3. Multiplying each, you get 4/21 x to the negative 2/3. Another pretty intuitive rule is the sum or difference rule. If you have a string of terms, all you have to do to find the derivative is take the derivative of each of the terms and either add or subtract them according to the sign in between. So if you have the derivative, or if you have the function here, and you wanted the derivative, y prime, 3x to the 5th, you're going to use your constant multiple rule and the power rule, 15x to the 4th, plus 30x squared minus the derivative of 4x is just 4, because x to the 1st, 1 times 4 is 4, x to the 0 would be 1. So the derivative of 4x is just 4. The 11's a constant, so the derivative of any constant is 0, so you don't write anything there, you just leave it as nothing. So y prime is 15x to the 4th plus 30x squared minus 4. Okay. Derivatives of trig functions. We're only going to focus on the sine function and the cosine function today. You have the graph of y equals sine of x, the graph of y equals cosine of x. We're going to start with y equals sine of x. We want to find the derivative of y equals sine of x. We're going to do this by graphing a couple points where the derivative exists. So y equals sine of x, remember the derivative is the slope of the tangent line. So the easiest tangent lines to identify would be tangent lines that are horizontal, that have a slope of 0. So if I look at this graph, you can see right here, you have a horizontal tangent line. If I drew a tangent line, it would be horizontal, touching right there, so it has a slope of 0. So the derivative, the value of the derivative, would be 0 right here. Right over here, you'd also have a derivative of 0, and over here again, another derivative of 0. Now we want to look between these points. If I look between these two zeros, the value between these two horizontal tangents, I see that the function, sine function, is increasing the whole time, is going up. The tangent lines will always be positive. So between these two, I'm going to be a positive. My derivatives will be above the y-axis. They start out not very steep, get pretty steep, and then slow back down again. So they get not very positive, more positive, and then back to less positive again. Now between this 0 and this 0, the derivative of all the tangent lines that you drew would be going down, would have a negative slope. So they start off not very negative, then they get pretty negative, then they start flattening out back again as they get closer to that 0. So your derivative would be not very negative, more negative, and then come back. And then it would repeat over here, and you see this red function is the exact same function as the cosine function. And it turns out if you did this perfectly and you found the limit as those secant lines, as the points of the secant lines got closer and closer together, in fact, if y equals sine of x, y prime would equal the cosine of x. So the value of the slope of the tangent line anywhere on the sine function is exactly the same as the value of the cosine function at that point. Similarly, as these are two graphs that are just shifted, horizontal shifts, the derivative of the cosine function is the sine function, actually is the negative or the opposite of the sine function. So if y is cosine of x, y prime would equal negative sine of x. And these two derivatives are the basis for the other trig derivatives that you'll learn the next time you do a lesson. So again, y equals sine of x, y prime equals cosine of x. If y equals cosine of x, the derivative is negative sine of x, the opposite of the sine. Sine and cosine are related. Last, now we learned some rules for derivatives. We'll often have to apply them to some problems where you have vertical motion, falling objects. So in any of your physics courses, you would have talked about position functions. Most commonly, they're denoted by an s of t. So s of t equals the position at some time, just like f of x, just using an s for your function of the t. And this is the general position function of any falling object. 1/2 times the acceleration due to gravity of t squared, of your time squared, plus v sub naught, meaning your initial velocity. How does it start moving? It starts if it's launched upward, if it's launched downward, if it's dropped from rest, your initial velocity times the t times your time, plus s sub 0, your initial height. Does it start at ground level? Is it launched off a building? Is it below sea level? Something like that. So this is your general position function. You're going to talk about average velocity and instantaneous velocity. If this is your position function, the height of an object, in order to find your average velocity over an interval, average velocity on A to B, so from 3 seconds to 7 seconds, or any interval, you're going to take the slope of the secant line to find out the average velocity or average speed over that time. It's going to be your change in your position divided by your change in your time. So you just plug in your values for A and B. The position at B minus the position at A. Difference of your y's over B minus A. The second time minus the first time over the difference of your x's. Just the slope of a secant line. Now when you refer to instantaneous velocity, that's going to be the slope of a tangent line. So it's going to be the derivative of your position function, or it can also be denoted as v of t. S of t is your position function. S prime of t or v of t will be your velocity function at any time t.